Okay, welcome everyone to the Australian German College of Climate and Energy. My name is Nick Parry. I'm one of the PhD students here. We have a very timely presentation today, given the release of the IPCC's 1.5 degree report. We have Tom Kompas is here. Tom is an environmental economist here at the University of Melbourne. He will detail perhaps some of his background before he begins. So without further ado, I'll hand it over to Tom.
Good. Thanks, Nick. Right. Good. Thanks, Nick, and thanks. Let's check the volume on this. We okay? Okay. Right. Good. I can talk softly then. Good. Thank you for coming, and thanks to those who are online for checking in. Pleasure to be here. I'm relatively new to Melbourne Uni, but I've known about this college for some time. It's my first visit here, so it's a pleasure. So thanks for the invitation. As Nick said, actually I'm an applied mathematician and an economist. I don't work in an economics department, and happy about that. I work in the School of Biosciences, doing mostly biosecurity work, but half my time is spent on large dimensional computational models. That's what I like to do, particularly when you have optimization routines pasted on top of them. Economists love to optimize. So we generally write models like that, where firms and consumers are doing the best they can, making decisions in response to market signals and other things they care about. The problem in that context, of course, is it's very hard to solve a large dimensional model when you're optimizing. And that's one of the messages from today. The bottom line here is, I think, in my view, economists have largely underestimated the damages from climate change at all temperature ranges. Even the celebrated DICE model, now celebrated DICE model, which received a Nobel Prize yesterday, or at least the person in charge of it did, and deservedly so, no disrespect here. For its day, it was quite innovative. Even that model has relatively small damages, even at extreme temperature ranges. 1% of global GDP, at most 2% of global GDP, which for an economist with a discount rate of 5 or 7% would mean nothing. Just wouldn't even bother. So the reason that I think economists have underestimated these damages in large part is due to the fact that their models are dimensionally constrained. They're small. The DICE model itself, early versions, had one commodity produced in each region across 20 regions. So very dimensionally small. And when you do that, when you collapse countries into regions, or you collapse commodities into a fewer group of commodities, you miss a lot of the extreme possibilities that go with climate change. So when you're looking at Asia, for example, as a region, and trying to determine a metric for the damages that might occur with climate change in that region, you're going to be averaging across all kinds of countries and missing extremes because of the nature of the averaging. I think that's basically it. You'll see a comparison today between our approach and the approach, I think the second best approach currently available by people named Rozan and Satori. Their model's dimensionally not as small as a DICE model, but it still misses a lot of this sort of variation that you get by averaging. I think that's driving most of the results. The irony here is that indeed the criticisms of the original Stern report, which is an exception to everything I've just said on the economics of damages from climate change, the criticisms of that, in fact, centered on the discount rate, if you know that sort of work, right? The argument from Nordhaus and others was that the discount rate assumed in the Stern report was far too small. So you get huge damages as a result of not discounting in a proper way. The actual discount rate is 1.4 in the Stern report. Economists need to discount. Okay? There's a big debate around this, but future dollars for economists are worth less than current dollars. So some interest rate has to be incorporated into the optimization routines to get a valid result. We can talk about that later. It is true that the Stern report uses a low discount rate, but we get the same and even larger damages with the 5% discount rate, which is more standard for an economist. So it's nothing about the discount rate in this work. Stern, in fact, had the magnitude of the damages roughly correct, with some qualifications, even with a small discount rate. That's unfortunate in the sense that when economists, in fact, when environmental economists looked at the criticism of the Stern report, I think they sort of switched off, right? Because they thought, oh, okay, there's not a whole lot of damages coming. We can think about other things. At least I suspect that's what happened. Turns out that that's an error. Turns out, in fact, that the damages are substantial, even if you use limited damage functions. Okay, all right, that's the pitch overall. I'm going to show you what it all means. If I can get this to work, here we go. So back to this issue of cursed dimensionality. It's not unusual in economics and even in other computational systems that are trying to optimize to find it very difficult to find solutions when the dimension, either spatially or temporally, is very large. These are large computational problems, and it's not even clear mainframes will solve many of these problems. Optimization techniques make it very difficult. It's especially true in the environment, and indeed in biosecurity, where I work, where you're tracking the spread of a pest or a disease in an environmental landscape with pixels that are very small. Very hard to optimize in that context. The same is true here. So our objective in this work, which we started a long time ago, is to try and find a computational routine that gets around this curse of dimensionality. Trying to solve a very large, what's called a GTAP model, an intertemporal forward-looking GTAP model, to try and track the effects of climate change in terms of the typical sort of trading patterns that would occur with damages from climate change. The model we're using here, the GTAP model standard. In fact, GTAP is more properly a database for us. It's a database of 140 countries across 57 commodity groups. Most economists will aggregate or average down to 20 commodities or 20 regions. We use the whole thing. Okay? We've got a way of solving this sort of computationally in a very large dimensional setting. But it's a standard approach. In fact, this model principally would be used for trade analysis. What's the effect of an announcement by Trump of a tariff on China? We'd plug it into the model and see what the effect is on income and GDP by country. You'd have to do that every other day because he changes his mind a lot, but you can still do it, right? That's its principal sort of use in a sense. We've now taken it and applied it to climate change. And I won't get technical today, but I will describe roughly how that happens. It involves the use of parallel processing systems and ways in which you manipulate a very large matrix. And I mean very large. These are systems with 500 million equations. So it's large. You have to find a way to manipulate that structure. What are CGE and GTAP models? These are the ways in which economists sort of model the global economy. They're standard. IMF, World Bank, Deloitte, Ernst & Young, every government agency uses some form of a CGE model. One of the best known ones is GEMPAC, which is down at Victoria University. That's common. That's something you can use. They have a set of software that you can use. But it's also dimensionally constrained. So these things are common. And what they are, they're really quite, in a way, easy to understand, but very complicated in terms of structure. In each country, you ask the question, across 57 commodities, what are the major inputs used to produce output of those 57 things? So you take land, labor, capital, natural resources, other intermediate products, and you combine them to produce output. And that output can be either consumed or invested. And consumers can either purchase that output domestically or internationally. So there's a flow of imports and exports here. There's a flow of goods and services around the globe, depending upon tariff conditions and non-tariff barriers. All that structure is there. There's a government, there's investment, there's savings, there's financial flows. This is why it's so big. It's a global model, which is country specific, thanks to the GTAP database, which comes out of Purdue, Indiana. So it's not hard to really understand what's going on here, but computationally quite difficult. And indeed, because of the dimension, a lot of standard approaches use simplifying assumptions to solve this system computationally. Very common to have static approaches or what are called recursive approaches, things that reduce dimension. Recursive approaches, for example, the one done at Victoria University, have price level assumptions that assume generally that people are forecasting future prices based upon current and past prices, what are called adaptive expectations. So it's not really forward-looking, it's backward-looking. That's done to reduce the size of the dimension. Because if you look forward, and you're trying to take into account future time periods, the dimension just gets larger and larger because you're solving this system not just today, but for periods in the future as far as you can. But there's a problem there, right? Price today means that's your best forecast of price tomorrow. It's not quite right, particularly when you're looking at climate change, when there are known, if not universally believed, effects coming in the nature of the Earth system. You need some forward-looking behavior. It's a price level assumption that's equivalent to saying, if it's sunny today, it'll be sunny tomorrow. For Melbourne, that won't work at all, right? Even if it's sunny this hour, it won't be sunny next hour. So it's not quite right. You need something that's a bit more forward-looking, more what we call in economics intertemporal in its approach. Sometimes those devolve into perfect foresight models. It depends on whether or not there's stochastic elements included, but forward-looking is really quite important. Some approaches don't even bother with a sort of dynamic setting. They just use static comparisons. What's the effect on GDP from climate change today compared to 2100, and compare them, without talking about the path of how you get from today to there, which again is not very satisfactory. The only sort of intertemporal studies that are available are the DICE model with a very limited dimension, and a couple around the traps, including one up in Canberra with a friend of mine. I used to be at ANU, Warwick McKibben, who has a G-cube model. Right? The largest of these is of intertemporal models has 10 regions and 12 commodities. And the DICE model, again, is even smaller. So we have a model, a system here, a computational system that has 140 countries and 50 commodities. So we're off the map in that sense. We're bigger in scale than anything available. Indeed, as I said, even the so envisaged model, which is used by IPCC as sort of the best going CGE approach to climate change damages, is limited in dimension, 20 regions. And it also adopts this assumption of adaptive price level expectations. Rain today, rain tomorrow. So there's something missing here. We need to do better. And that's the point of this work. You can see why economists have trouble, right? Because you're trying to optimize, firms are maximizing profits. They're finding the best rate of return on investment. Consumers are trying to allocate their income across goods in the way they think is appropriate and best for them. Because you're trying to optimize across the big dimension, you have real problems trying to solve the system. You can see why. This comes from the version 7 of the GTAP database. One we don't use, but it's one that we calculated here. If you keep region size unchanged from 1 to 6, but increase the number of commodities from 3 to 57, this is what happens to the number of endogenous variables. Okay, 500 million is easy to get for 47 periods. And if you're going out to 2100, you need more than that, right? If you're going past 2100, of course, you need even more. So dimensionally, very hard to solve computationally. And again, that's why economists aggregate, average, embed price level assumptions that allow you to move not through time computationally, but period after period after period with naive price level forecasts. I want to talk about the current software that's available. GEMPAC is the best going, I think, in many ways, along with McKibben's G-cube model. But what you have to do to solve this sort of system is manipulate a big matrix. It's really quite simple in a way. You get what are called first order conditions for optimizing. Right? People allocate their incomes across goods in a way that they see appropriate. Firms hire inputs depending upon factor prices to minimize costs. You get all these first order conditions, and it lapses into a big matrix, you know, with more than 500 million variables and equations. Huge matrix that you have to manipulate to solve. So you have to carry a lot of things around. If you do it just, if you construct that matrix just using the standard GTAB database, you get a lot of, you get a lot of holes, what are called sparse elements in the matrix, and you get a lot of material, a lot of things scattered around. And that means when you, in fact, take this matrix and run it through your system, you have to carry all of the missing information as well as the information that's in fact relevant to you. So it just makes things impossible to solve. And these models generally crash. Even GEMPAC, its dynamic recursive model, will crash with 30 commodities or 30 regions, even though it's not forward-looking or intertemporal. Right? So what we do, in effect, this is just a graphical representation. Pretty hard to describe 500 million equations in a PowerPoint. Right? What we do is we arrange this matrix in an appropriate way using techniques we've developed over the years so that we get something that's a little bit more ordered that we can in fact then use and manipulate to solve. And in fact, when you combine that with parallel processing techniques, you can take chunks of this reordered matrix, solve them separately, and then bring them back together. That's the key. And indeed, this model is still solved on a module up in Canberra and in my apartment here in Melbourne with 10 computers networked, solved in parallel using that system. You can do it. It takes some time, but it's possible to do it even with a personal module. And when you do it that way, right, these are the computational times you get. The current technique we use is this nested technique, which you don't have to know about. But you can see when you get a larger model, this is model 6 with 47 time periods, 112 countries, and 47 goods. This is the computational time using our algorithm. You can solve it, which is good. Our older techniques couldn't solve big models. The new technique can. Using these parallel processing platforms, and you can solve it in this time period. How long is that? What do you think? It's about 27,000 seconds. That's about 8.5 hours. So it'll solve in about 8.5 hours. You extend the model, of course, it just gets longer and longer. But it's not as bad as you would think, as you might think, in fact, because of the nature of the solution algorithm. Okay, so that's the technical stuff aside. I want to talk about the climate damages now. Okay. So we use the GTAB database, 140 countries and 50 plus commodity groups. We also, to find the damages, use the existing database by Rozan and Satori. So we're not, in a sense, using anything different here than what's available commonly. We're just using a better computational algorithm to get a finer result, and it makes a big difference. In the end, dimensions everything, I've come to understand. Rozan and Satori have climate damage functions that they've assembled, you know, for some time. They're used by IPCC and other people. They focus mostly on loss in agricultural productivity by country going forward. Also a bit on, of course, on labor productivity. There's some health effects included, and there's sea level rises and hence loss in arable useful land. So you get sea level changes, you get agricultural productivity shocks, you get human health effects, and that's basically the extent of the damage functions. This is really good work. It's the only thing available to economists, and in fact, generally available in terms of damage functions. But it's limited, right? It doesn't include the effects of pollution, doesn't include fire and floods, it doesn't include the sort of tropical storm events you might get with climate change. We're working on that now in a stochastic version of this system. It leaves all of those things out and just focuses on these limited sets limited set of potential damages. Indeed, agricultural productivity really drives a lot of the results here with extreme temperatures. So what we do, I'm not a climate change scientist, clearly I'm not, you should know that. Computational person. But what we do is we take SSPs and we map them into RCPs and temperature values and ask the question in terms of these damage functions, what's the effect across a number of different countries in this data set by commodity groups? The reason why it's important to do it in this context is because you have a trading mechanism. Right? When there are damages that affect countries differentially, there's different trading patterns. Exports and imports change, so incomes change. Everything changes. And if you don't capture the full extent of that, you miss a lot. At least the economist misses a lot, but also the measures of economic damages, again, will be understated if you don't capture that sort of complexity. So we concentrate on business as usual and just look at 1 to 4 degree. In fact, in this presentation, I'm looking at 3 and 4 degrees, which is a disaster in many senses, and compare it to a benchmark in the Paris Accord of 2 degrees. I've given up on 1.5, so I'm just focusing on 2 degrees here. So we can talk about that, all right? Okay. The commodity groups, and we can do it for 1.5, it's not a big deal. The commodity groups in this GTAP system, you can see they're fairly, I didn't put all of them down here, but they're fairly varied. They concentrate a lot on agricultural outputs, so that's very common. But they also include a lot of energy components as well. Indeed, quite a few energy components, financial systems, manufacturing, transport, chemicals, rubber, leather. There's all kinds of things in the 57 commodity groups. And the goal, again, is to find the damages from climate change as a result of different, with business as usual, temperature ranges. So we run the model, large dimensional, 500 million equations, run the model and ask the question, what's the effect on trading patterns? What are the damages that occur as a result of having different temperature ranges? And we start with, as a benchmark, the 3 degree case. Okay. So I can show you all of that. Computationally takes some time, but these are the results. So you start, the way the model works, the model output here generates percentage falls in GDP, which as many of you know is a fairly narrow measure of welfare, but it's the one that economists like to use. It's the measure of GDP. So you're asking the question, what's happening to incomes around the world by country as a result of changes in trading patterns, temperature changes which cause damages as a result in agricultural productivity, labor productivity, human health, sea level rise. You can see after 10 years, you're not getting, the pink is starting to show up in Africa, but you're not getting, remember, these are limited damage functions. You're not getting a lot of action. I'll show you actual numbers in a minute. 20 years, it starts to pick up. 50 years, more so. Long run impacts, you start to see a pattern. You start to see that, again, I'll show you numbers in a minute. This is at 3 degrees. You start to see that most of the substantial damages in this economic model occur around or near the equator, as you might expect if you work in this area. With significant damages clearly in Africa and Asia, particularly Southeast Asia. The Antarctic here in this data set is bundled together with Pacific Islands. So there's no fall in GDP in the Antarctic, okay? It's just bundled with Pacific Islands. Not my call, GTAP's call. So in fact, this is trying, since you can't have resolution on Pacific Islands, this is a nice way to sort of capture that effect. That's what they do. That's the 3 degree path from now until 2100. Right, so these are, in effect, the long run impacts in 2100 in terms of percentage GDP. Later, I'm going to show you the cumulative impacts. These are the long run impacts. You get to 2100, this is the effect on GDP. Before we get that though, let me compare the second best going computational model to our model. These are the results that come out of Rozan and Satori's climate change model, using first order effects, what are called recursive functionals, so that sunny today, sunny tomorrow sort of platform, and somewhat aggregated. So the comparison's not invidious, but it's a little bit, it's tough to make comparisons, but you can do it. You can see the fall in GDP for us, this is, I'll talk about what these numbers mean too in a minute. The fall in GDP is always substantially larger than the first order effects. Sometimes 2 or 3 times larger. And indeed, if you go to 4 degrees, the extreme case, the differences get even larger. And all of this is larger than the sort of Dice-Rice model, which never get past 1 or 2% in global GDP damages. So that's important to keep in mind. So that's my point, the point I started with. Economists have largely underestimated these damages. Even the second best going model still underestimates the damages considerably. I'll show you what that means. The more simplified models, in fact, severely underestimate damages. This is what happens if you vary temperatures. You can see this is the number we just looked at, the 3-degree temperature range. If you just go up a degree, you get, of course, substantial damages. This is trillions. These are in $1 billion. So this is $23 trillion global damages. Close to the Stern report, in fact a bit larger. These are 9 trillion damages, 3 degrees, and 2 degrees is still significant at 5.6 trillion. And you can see, again, most of the damages occur sort of in the equatorial zones, but you pick up the United States and Japan and some other cases, even Australia is picked up in this case, and certainly in the 4-degree case. I'll talk about that in a minute. That's what happens if you project this model forward using SSP2 baseline case, business as usual, 3 degrees. This is 3 or 4, 2 degrees in 2100. So that would be a loss of 23 trillion every year in 2100 in perpetuity. It's not a one-off loss, it's every year in perpetuity. So what does that mean? I sometimes have trouble counting the zeros in this work as well. There's a huge number of zeros. What does it mean? Yes. Well, they're substantial. Even at 3 degrees, they're substantial. 4 degrees, they're catastrophic. So if you like, the $23 trillion figures, at least 3 or 4 global financial crises from 2008 each year, every year, at least that. There's a lot of debate about the actual cost of the GFC. So I'm taking a conservative number here, but it's about 3 or 4, I think a bit more. So you have that every year, year after year. Some countries, the losses are especially severe. You could see that Africa really gets pounded here, but so do others. Indonesia, 19% fall in GDP, India, 14%, Philippines, 20%. Much of Africa, my good friend, ranges from 18 to 26%. Huge falls in GDP. What does that mean? The fall in GDP in the Great Depression globally was 15%. Okay, so if you're talking about 20s and teens and 20s, you're talking a repeatable Great Depression year after year. This is what Pursuit at Melbourne Uni picked up and put in the media. And I'm happy to say got all the way to the New York Times, which is really quite nice, given where I come from. Okay. The failing New York Times, excuse me. In Australia, Australians often ask, and these are the damages at 4 degrees. They're not trivial, right? It's about 14,000 per household at 4 degrees. Again, remember, with limited damage functions, no fire, no flood, no pollution, of course. So you start to really worry. If you get those numbers, it's easy to see what the effect is, the gains, if you like, from complying with the Paris Accord. I was in France just 2 or 3 weeks ago, and it's a big message for them, I think. If you compare the scenarios at 4 degrees relative to a 2-degree target, you gain 17 trillion. That's in 2100 going forward. At the smaller target, 4 trillion, which is about a GFC each year. So not too bad. It's a lot of damages. So complying with the Paris Accord from an economic point of view means a great deal. And this is counter to the way in which economists talked about it, at least initially, when the Accord was being debated. Richard Toll, Bjorn Lomborg, other people were highly critical of the Paris Accord for this reason. We'll talk more about that in a minute. Now, let me talk about the cumulative gains, cumulative losses. So what I did just now is a projection from now to 2100 and asked the question, what are the damages then? Well, what are the cumulative damages from now until 2100? We need to know at different temperature patterns. This is, I took the, the rough case, the 4% case, but it's also bad for the 3% case. You can see that, again, there's a sort of equatorial mapping of the damages, but you start to pick up significant effects in various other countries. This may not look like much, but in fact, if you have a big impact in the United States with the size of its economy, it's really quite substantial. This is done in billions of dollars. Here are the numbers. So at 3 degrees, about 271 trillion. At 4 degrees, the cumulative effect is a whopping $604 trillion. And indeed, it goes all the way down. You can capture a lot of these negatives all the way down to Australia. There are some countries that gain. Put them on the slide. France gains, UK gains, Germany gains, relatively small compared to their GDP. But that's the nature of these models, right? Because when you get severe damages across the world in particular zones, it changes trading patterns. And in fact, incomes, in fact, may be better off in some parts of the world, slightly so, compared to the global amounts or particular countries. We can talk about that. Yeah. Now remember, this is just damages. This is not an integrated assessment model. We're very close to doing that. It's just damages, right? But it'd be hard to imagine it. You couldn't find an emissions reduction scheme that's less than this amount, 604 trillion or 300 trillion going forward. Trust me, it's far less than that amount. Okay. Also, a nice little graphic before I sort of start to close off, a nice little graphic on the effects here by region, by country, particularly by country, by income. So it's a little bit fuzzy, but this is income on the bottom. This is impact in terms of damages. The circles are individual countries. And the size of the circle is the size of the population. So this is India. I believe this is China. The United States is out here, out here. That's the sort of graphic that you're looking at. The size of the circle is the size of the population. You get what people often talk about from this computational approach. The result that most of the damages, most of the impacts, in fact, measuring impacts here in terms of percentage changes, most of the impacts occur in the poor, quote unquote, part of the world. When indeed most of the damages indeed are created in the richer part of the world. So you get a huge ethical issue here, particularly when it comes to a country like Africa or Southeast Asia, which doesn't emit a whole lot of carbon emissions and actually bears most of the damages from this sort of exercise, from the way in which we're handling something like SSP2. Though, final thoughts. So averaging across countries just doesn't work. You miss the extremes. The old story, right? You try and cross a stream that on average is 1 meter deep, you're fine, but there are some parts that are 4 meters deep. You have trouble. Averaging misses the extremes, so you miss the impacts that go with it. Remember that damage functions are limited, so we haven't even captured things like storms. We've got a paper coming on that. It's really quite nice, a stochastic version of this. And it's quite clear that what we're not picking up, along with pollution and fire and flood and tropical storms, is the severe disruption that goes with individual countries. If you have a 20% fall in GDP or more, your government collapses. If you combine the fall in GDP and the tax revenue that comes with that, with emergency response with fire and flood, you really collapse. So it's not very good. It's a very bad outcome. Actually, yeah, very bad outcome. Final slide, and then some final comments, and I'll be done. So I think when I've been doing this work, I've sort of been capturing what I call the 3 great myths in the economics of climate change. Not all of them are captured in this presentation, but some are. The first myth is that long-run damages, both in 2100 and cumulative, are relatively small. both in terms of volume and as a percentage of GDP. That's just wrong. And indeed, the original criticism of the Stern report, because of its low discount rate generating large damages, is misguided, not right. The second myth, it's often said, Richard Toll and others, that poor countries are not that differentially affected, except at extreme temperature values. We show even at 3 or 4%, that's not true. Even 2%, they're severely affected. And indeed, they make the case, well, look, they may be affected, but we can compensate from rich countries because we can continue to increase GDP and then have a compensation mechanism to make them just as well off. Well, at 604 trillion, it's a hell of a compensation mechanism. You just can't do that. The amounts are way too large. The third one that we're working on now and trying to develop our own IAM is the cost of emissions reduction. This is the Born-Lundberg sort of view of the world. Okay, there may be damages, we admit that now, but the costs of sort of emissions reduction far outweigh the damages that occur with climate change. I'm sure that's not true. Again, it'd be very hard to find an emission scheme that's more expensive than 604 trillion. What's missing here? It has deterministic elements because of its size. Got a stochastic version coming, which is very hard to solve computationally if you work in that sort of area. What's also missing, of course, is the integration of the various energy and power components. So fortunately, there's a GTAP-E energy, GTAP-P power data set. So we can take this work, combine it with those data sets, and actually have a fairly decent integrated assessment model. It still won't pick up fire and flood and storms or pollution because the damage functions are still fairly limited. That's the Achilles heel here. But even with these limited damage functions, it's an alarm. It's a call to action. You can't think of it any other way. Good. Thanks for listening.
Thanks, Tom. Rolling depressions, collapse of governments, and you describe that as a very bad outcome. It's a typical understatement from an economist, I think. We'll now open the floor to our questions. We'll start with Malta.
It's catastrophic. Okay, I just don't want to be alarmist. I'm often accused of that, but in this room, it's catastrophic. It's the end. The planet is bad enough, of course, but the economics here are really severe.
Thank you, Tom and Malte, and sorry for being a little bit too late at the beginning, so I missed part of it. But...
Yeah, you missed my big pitch. It's okay.
At some point, you aligned RCP 4.5 with 2 degrees.
Yeah.
Normally, for Paris Agreement, RCP 2.6, the next lower scenario is aligned with below 2 degrees.
Right.
Why have you made that choice, and would that affect your columns in terms of is your 2 degree warming scenario the RCP 4.5 case, or is it something else?
It's the 4.5 case. So it's not yet a fully integrated assessment model. So we were a bit coarse. We're developing an assessment model now that captures that information so that you're able to, in fact, really map nicely SSPs into RCPs into temperature changes. For now, in the first half of this work, which is in its future, right, we just asked the question, what's the effect on temperatures in terms of damages? That's what's being done here. And tried to casually map in SSPs. I think it's about right, given the IAM that we're constructing, but that was the first pass. So, yeah. Quite right. And we focused on 2 degrees just in a sense arbitrarily, right? I had the view at the time when we were doing this work that 1.5 was impossible anymore. You can correct me. I'm happy. I'm sure it is. Of course it's possible. But given the way the world works, remember I come from Trump land, given the way the world works, it didn't seem possible to me. So I just picked 2, 3, and 4. So it's that simple. The second half of this paper, in fact, takes model output and uses IMF forecasts in 2017 to project forward based upon SSP2, business as usual, to get the dollar amounts. So that's good, but it's not good enough. So we're racing now to do an IAM to sort of bring all of that together so that we can, in fact, get proper sorts of estimates. Yeah. And we're almost there. The problem, though, of course, as you'll know, is that you have to include the power mix and the energy mix. So you're asking questions: what happens if you switch from fossils to renewables? What kind of renewables across 140 countries, right? With a time scale that's out to 2100. It's not trivial computationally. It's not even trivial conceptually to do. That's why things like the Dice and Rice model are so popular, because they're so small scale. You can do these thought experiments, much more easily. In fact, it's available for free online. But my point is, if you don't capture the dimension, you miss everything. If there's an approximation error, if there are errors in this sort of approach, I can guarantee the errors in the smaller dimensional model far swamp our approximation errors. So, yeah. So that's, have me back sometime when the IAM is done, almost done.
Thanks, Tom. That was great. I'm Rebecca Burden. I've just started with the Energy Transition Hub. When you talk about integrating the power and the energy sector, when they do it for country-specific analyses, like we've done in Australia in the past, they've used sector-specific models in conjunction with things like MMRF. Is that, could this model be used in that way with sector-specific models to capture country-specific effects and the dynamics of those sectors?
Have a look at GTAP-E and GTAP-P. It's exactly what it does. These are databases that are really well constructed. They've been going on for decades and decades. Add country specific, absolutely. And indeed, you can take much of that and drill down to within country specific effects, right? We use these sorts of models to, in fact, back out global results and then run a separate GTAP CGE model for individual countries. Got a nice paper on Vietnam for that. With sea level rise, the Mekong River Delta, as you know, disappears. We know the effects there. We can calculate what's going on. You can do it for energy as well. There's some issues and problems, but it's really a nice data set. It's the best thing to do, I think, going forward. And it's a thing that, again, the sort of standard Nordhaus kind of models don't capture well. Yeah. You've got this big data set developed by Purdue. Why not use it? That's what we're doing. Thanks.
I actually have a question, and I have a microphone, so I'm going to use that. My question is in relation to the implications for policy making. And you yourself have acknowledged that it's you're sometimes considered alarmist and potentially presenting a very alternative view from the mainstream in terms of Nordhaus, and bearing in mind the critique of the Stern report, which found similar results. Do you have any comment to make about how you then influence or impact the policymakers in terms of presenting this in a way that allows them to appreciate the potential catastrophic situation in the face of opposition is not the right word, but hopefully you appreciate what I mean.
Yeah, I've got too much experience there. But I can tell you get a lot more traction these days in Europe than used to be the case. A good friend of mine, Andrew Lee, in Parliament is very keen on this work. So if there's a new government, I think it'll have some traction. The current government's shocker. It's incredibly bad. So I get the usual sort of thing, tons of emails and bad emails and criticism. That's fine. I don't care. I mean, we have a model context that I'm quite proud of. It's very large dimensional, solved uniquely for the first time in terms of how economists approach this problem, and these are the results. And it's quite clear something needs to be done. We don't transition. I think if you look at the preliminary version of the IMM we're building here, you need even quicker transition than the current summary of the IPCC, which is the only thing I read so far. I think in fact you need even quicker transition out of fossil fuels. So yeah, won't be friends with people at Exxon or whatever. That's fine. It used to be that, people who said, oh, 2100, oh, that's too far away. You get this a lot. You get this in the press in Australia when this came out. SBS did a little story on it, but they're going, oh, it's 2100. But someone born today will likely live in a well-constructed world, assuming we don't have these meltdowns, to 2100. It's not that far away. And the cumulative damages drive the point home. They don't really start kicking in until 2040, 2050, but they kick in, and they're severe. I didn't answer your question, really. Let's chat. Yeah.
Thanks for your talk. I came in late. I'm Ian Blair. I'm an agriculturalist. Now, the question I ask is whether your model takes into account, for instance, the Meadows model of the beyond the limits, where phosphate and some of the nutrients and things were going to be limiting factors, water, another one. And then I've just been to China in November, and their soil pollution, air pollution, and water pollution, I think will nobble them before they get some of the other things. So some of these moves are so rapid and quick that they might be all over by before 2100.
So a really nice point. It's a point that a friend of mine, Quentin Grafton, up at Canberra, at ANU makes as well. He works on water quite a bit. The answer is it doesn't take it into account. Okay, there are no pollution effects here. There's nothing that you described, and that tells you something really quite serious. Because if the damages are severe here, they'll be especially severe when we start to incorporate your elements. And indeed, the integrated assessment model we're currently working on has no assumption about peak oil, has no assumption about anything with regard to fossil fuels. It's as if you can just run that for 200 years, and we know that's not right. Right? So, there's a lot of work to do to get this right. In fact, every conference you go to, you hear the same sort of thing. The real problem with work like this, even though you're getting big damages, the real problem is that the damage functions aren't well constructed or understood. You need more damages to get a better picture. So we've started on a tropical storm version, and basically the damages increase by about 40%. Okay, so you get big impacts. That's a stochastic version of this model. If you were here criticizing this model, you'd say, okay, it's deterministic, blah, right? But you can do a stochastic version, computationally very difficult, as you can imagine. But, so you're right. The effects on soil, the effects with water, they're severe, particularly in countries like Africa. That's not counted here. It's indirectly, some of it's counted because the fall in agriculture productivity is trying to pick up some of those effects, but I think a lot of work needs to be done. It'd be great to have an army of people working on damage functions in a proper way.
And I'll just add one other thing which hasn't been taken into account is the people effect. Now, India is losing 150 million farmers in the next 10 years. They've got to train them agriculturally. And China's moving 70 million farmers off the land to do a revamp. Now, one, that's going to take a hell of a lot of energy, hell of a lot of training, but are they capable of feeding their population while those massive changes take place in their population and demography?
Exactly right. So the Rosanna and Satori damage functions include a bit of human health effects, a bit of displacement, but nothing like you just described. Yeah.
Have we got any more questions? Tom, I think you'll be sticking around anyway.
Oh, good.
Yeah. So you talk about a 6% discount rate. I think our political discount rate is about 95% at the moment, unfortunately. But I'm doing a case study on the UK, and I know the Stern report, for all its flaws, had a significant political impact. So hopefully some of your work has a similar impact in this country.
I hope, well, I'm not hopeful about this country yet, but yeah, but other parts of the world, I hope so. Yeah, indeed. Thanks.
You certainly dented my optimism a little bit today. But anyway, the sun's shining, and as I said, hopefully we can turn it around. So just a note on our next event, Monday evening at 6 o'clock. I think it's in the Kathleen Fitzpatrick Theatre. It's a joint event with Amos. Thursday. It's tomorrow. Check my calendar. So this is a panel discussion on the 1.5 degree report that came out from the IPCC. So very topical, obviously. Some great speakers. So if you can join us tomorrow night at 6 o'clock, that would be great. Otherwise, keep an eye out on our Twitter or our website for future events as well. Big round of applause for Tom.